much, Iman, for the introduction. Today I'm going to speak about the superconducting nanowire single-photon detectors and multi-photon detectors. First of all, I would like to thank our team members and collaborators who contributed to this work I'm going to present, including the current students in my lab at Tianjin University and the students who were in my lab. They have already graduated, and our collaborators. We mainly collaborate with Professor Val Zuiler at KTH and his team in KTH, TU Delft, and single-quantum. And also, I would like to thank our sponsors for financially support our research. So first part of my talk is superconducting nanowire single-photon detectors, in abbreviation SNSPDs. You may have already been using those type of detectors. So a single photon detector is a device like this, okay? If the input is a single photon, it will signal output, which is typically voltage pulse. By counting the voltage pulses, we can count photons. So this looks very simple. And for SPD, the basic structure is like this. It is made of niobium nitride, niobium nitride thin film. Typically, the film thickness is about 10 nanometer or below that. Patterned into this serpentine structure, the blue part is the active area. And the width of nanowire has to be below 100 nanometer and covering area of 10 micron by 10 micron. So this is really a nano device, a small device with large impact. I would say that SPD is a pretty successful technology because they have been widely used in communication, computation, sensing, and measurement, including classical and quantum applications. Okay, I'm going to present in detail a specific example, which is an experiment I did when I was a student at MIT with Franco Wong's team. This is a polarization entanglement distribution. The experiment was done about 10 years ago, okay? At that time, I only built one SNSPD system with a single device inside to detect photon pairs. So that we use a trick called time multiplex coincident counting, okay? Basically, we delay one photon and then combine them, send to the niobium nitride SPD one by one. But as a result, we got 99.2% whole model interference visibility, and 150 times higher coincidence rate compared with using two in-gas detectors. So this experiment was done 10 years ago really shows the power of SNSPDs. How does it detect single photons? As a user, okay, you just need to, it's very simple. You just need to send a bias current into this nanowire and increase the bias current towards this switching current, okay? For example, you can bias that 95% of its I switch, then you will get very decent detection efficiency. This 24% is 11 years ago, okay? And a few dark counts as noises. In detection mechanism, the initial insight is called normal core hotspot model. So basically, you can imagine the superconducting nanowire as a little channel with supercurrent inside. A photon absorbed will generate a resistive region called hotspot. And due to the electrothermal interaction, the hotspot will expand and blocks the current. The current gets diverted into the 50 ohm line in parallel, generating a voltage pulse. And then due to the cooling, the resistive region disappears and it recovers automatically and ready to detect the next photon. So it can be operated in the free running mode. But the normal core hotspot model cannot explain all the experimental observations. So later, many models has been developed, including diffusion-based hotspot model, photon-triggered Vortex-Entry Model, diffusion-based Vortex-Entry Model, and normal core Vortex model, etc. So basically, somehow, people believe that Vortex got involved in the detection process. But one important comment is, I think the specific mechanism probably depends on the specific geometry of the nanowire and energy of incident photons. And so far, there is no such a model can explain all the experimental observations. I'm going to explain to you Vortex-Entry Model. So for that model, okay, the detection process is composed of 2 stages. So the first stage is a photon absorption, and the vortex enters the nanowire from the edge and creates a weak link on the transverse location X. So the second stage is really the electrothermal evolution. So the basic resistive region expands and shrinks and generate the output voltage pulse like this. Okay, keep in mind there are 2 stages. We use several numbers to characterize the detector performances, including the efficiency. So due to the hard work of the community, okay, several teams have demonstrated over 90% system detection efficiency at the telecom wavelengths. Now, recent time, it determines how fast the detector can take the photons, and timing jitter determines the timing resolution. Okay, recently, sub 3 picosecond timing jitter has been demonstrated, and dark count rate. There are noises in dark counts, but SPD has very low dark count rate. Can be a few counts per second, even sub counts per second. Okay, so in this talk, I'm going to focus on efficiency and timing jitter. So for efficiency, I'm going to talk about the polarization dependence of the detection efficiency and our work on the polarization insensitive detectors. So these slides basically explain to you the region of the polarization sensitiveness. Okay, so the nanowire, the classical structure of nanowire detector is like a wire grid, metal wire grid polarizer. Okay, those are 2 polarization, orthogonal polarization mode in optic fiber. They will dominantly respond to this polarization, which is TE11Y. Okay, has a high efficiency. But for the other orthogonal polarization, it has a lower efficiency. For some applications, we want polarization in insensitive detectors. To do that, our idea is called fractal SPD. Okay, we use fractal space filling curves. In mathematics, those curves are called piano curves. This is the first order. It's like an S shape, and repeat in space 9 times. Okay, this is second order piano curve, and third order, so on and so forth. We can expand the active area if we want. So, and we further optimize the device structure using a thinner, narrower nanowire with a width of 40 nanometer. And this electrical structure is called cascaded 2 snaps. We use 16 such units connected in series. Okay, 1 unit is 2 nanowires connected in parallel. Okay, after those optimizations, we really get 60% system detection efficiency with 1.05 polarization sensitivity. This is a quite low number, and below 220 counts per second dark count rate at telecom, 1550 nanometer wavelength. Okay, and also we measure timing performance, in particular timing jitter, and compare the timing jitter of cascaded 2 snap with a standard SNSPD. We got a 45 picosecond timing jitter for our fractal snap. And the Kai presented a poster about the fractal SNSPDs yesterday, so you may have already read our work on that and interacted with Kai. Okay, then I'm going to move on to talk about timing jitter and why it matters. Just be clear. Let me define timing jitter. So it is the varying time delay of the output voltage pulses relative to the incident photons. Okay, we can measure those time delays and do statistics like a Gaussian distribution. Use a full width at half maximum to quantify the timing jitter. It is important because timing jitter determines the shortest fluorescent lifetime that an SPD can measure, determines the spatial resolution. In a laser ranging system, we use SPD as a receiver. So that's why we need to reduce timing jitter. But for a long time, researchers in the SPD community do not quite know what induces timing jitter, the mechanism. Okay, so the first culprit that researchers discovered is electronic noise-induced timing jitter. So this shows the ideal rising edge of the voltage pulse. This is the rising edge with noises, with a little bit of exaggeration, okay? So the idea is the amplitude jitter along the y-axis will project to the x-axis, timing axis, okay? And the amplitude jitter and timing jitter satisfy this triangle relation, and K is the slope of the rising edge. And then later, MIT team, led by Professor Carl Berggren, discovered transmission line effect induced timing jitter. So basically, the nanowire serves as a transmission line with a quite low signal speed. It's about 0.2% or 0.3% of speed of light. Okay, so if a photon is absorbed and detected at P1 location, okay, there is a little delay, and if at the P2, it takes longer time for the signal to travel to the readouts. There is longer delay. Therefore, there is a distribution of the delay and uncertainty in the timing. So that's the transmission line effect induced timing jitter. Okay, and the third one is the final fluctuation induced timing jitter. And the final fluctuation is a quite universal phenomenon in electronic system. Basically, the energy of the photon deposited into the electronic system is a distribution, and the time delay is dependent on the energy deposited in the electronic system. So next is vortex crossing induced timing jitter that we discovered. Basically, it's due to the photons absorbed at different transverse location x0. Okay, so photons are absorbed at different transverse location x0, resulting in a different time delay for the vortex to enter the nanowire, which is T1, and also to go across nanowire, which is T2 minus T1. Therefore, there is a varying total time delay, T2, okay? Simply due to the, it's a distribution of the location where photon is absorbed at the transverse location of the nanowire. We simulate the vortex crossing induced timing jitter and estimate it's about 1 picosecond. Of course, it's dependent on the width of the nanowire. But this is we believe this is lower bound of timing jitter of SPD, and our paper is published in 2017. And then later, JPL, MIT, and NIST team, they jointly did an experiment and achieved 2.7 picosecond timing jitter. And the paper recently appeared in Nature Photonics. So the timing jitter mechanism 5 is also contributed by us. It's an inhomogeneity induced nanowire. Okay, so the nanowire looks very uniform, but microscopically there has they have inhomogeneities, including geometric inhomogeneity in thickness and width variations, and also electronic inhomogeneity. That is the superconducting gap delta varies along the nanowire y direction. Okay. However, think about the nanowire. If there is a long nanowire, for example, connecting Tianjin and Berlin. Okay, this is a very long nanowire. But the photon detection, single photon detection, is really dependent on the local property of the nanowire where the photon is absorbed, as well as some global property of nanowire, including the kinetic inductance and so on and so forth. Therefore, if a photon is absorbed here, it generates voltage pulse, but like this. But second photon is absorbed at the second location, it generates another voltage pulse, which is different than the previous one. Okay, the third place and third pulse, and repeat it 1,000 times. We did a so-called electrothermal Monte Carlo simulation and get this figure. Okay, so those 5 mechanisms are really the timing jitter mechanism that researchers has illustrated so far. But the key question is, based on those understanding, how can we reduce timing jitter? It's a difficult problem, actually. We go back to this triangular. Okay, so some timing jitters are intrinsic. Okay, some of them non-intrinsic induced by noises and inhomogeneity sector fluctuations. Of course, we need to reduce sigma n, which are noises, fluctuations in homogeneity. But we shouldn't forget another law, which is the rising edge, the slope of the rising edge. We should increase k. Okay, to increase k, we need to increase the switching, the bias current. Okay, by increasing W and D. In this way, we can increase k to reduce the timing jitter. But you will find that it is difficult because increase W and D, it reduce detection efficiency. Okay, so it is a challenge to simultaneously achieve high efficiency and low timing jitter. It requires very careful engineering of the film and also the fabrication process, etc. So recently, our chair, actually Iman, has done a nice experiment. We are the collaborators, and Iman demonstrated a system efficiency of 85%, and simultaneously with the timing jitter of 7.7 picosecond at the wavelengths of 950 nanometer wavelengths. This is really a demonstration of high efficiency and timing jitter at the same time on a single device. Okay. Then I'm going to move to the second part of my talk, which is the superconducting nanowire multi-photon detectors. In abbreviation, I call it SNMPDs. So what is the multi-photon detector? Okay, it's such a device. So if the input is in photons, okay, if it outputs signals, then it behaves as a n-fold coincident contact. If output number n, okay, tells us, you know, the number n, it is a photon number resolving detectors. So multi-photon detectors are including those two types. So first of all, coincident contacts. A straightforward way to count coincidence is really, you know, n-fold coincidence. We use n single-photon detectors, for example, SNSPDs. So that would be a very expensive system, and also it's difficult because of the thermal budget of the crowd cooler, etc., etc. So our idea is to use one SNMPD multi-photon detector with a circuitry as simple as one SNSPD to do the task. Okay, let me tell you how to do that. So this is our idea and the schematics of the device structure. So in the device structure, it includes n photosensitive nanowires, N1, N2, and N. And also wider nanowire behaves as a current reservoir. Okay, I'm going to explain to you. They are all connected in parallel, and then they are connected with choke inductors. Okay, the important part are N1, N2, Nn, and R. So the central idea is to use the supercurrent in the reservoir to temporarily store the information of the photon detection events. This is a fabricated or synthetic case of SN2PD. You can see N1, N2, and R. Let me explain to you the operating principle. This circuit of the device. Initially, we bias the entire device with IP, and the allocation of the current is according to the inversely proportional to the kinetic inductance of that branch. Okay, and when the first photon switches the first branch of the nanowire, the current flows to the current reservoir according to the design. Most of the current, okay, and a small portion flows to other photosensitive branches, okay, and at this moment, the current reservoir doesn't switch, okay, and then the second photon switch the second one. We repeat the process until the nth photon switches last one, the nth photosensitive nanowire, okay? That serves as the last straw. The current get diverted to the current reservoir and switch the current reservoir because it exceeds the current in the reservoir exceeds the critical current, okay? Then all the superconducting nanowire switches, the current has to go to the impedance Z0, generating voltage pulse, okay? Let me show you a video of this simplest two-photon coincident contact. Okay. See the first photon switch the first nanowire, there is no voltage output. The second photon switch the second nanowire, and now all of them get switched. They generate voltage pulse. So consequently, 2 photons, we get 1 voltage pulse. That's a 2-photon coincident counter. Okay, then we extend this concept to more photons. This is, to 8 photons. Okay, 1 voltage pulse. So notice that we have ladders here. Okay, current ladders. If we can read out those ladders, we can count the photon. Those are PNRDs. So we integrate the current reservoir with a Ytron. So this is a device invented by MIT to non-invisibly read out the current in the reservoir by measuring switching current of the reader. And the first photon, we generate the current in the reservoir. Second, different cases. So 2 photons on the nanowire is another steady state, and so on and so forth. So for SN2PDs, it can resolve 4 photons. The keys we need to resolve, have sufficient resolution to measure the current difference and sufficient dynamic range. And so this is a summary of the SN2PD. Those are steady state, and this minimum delta IR we need to resolve. And we extend this to more branches. Okay, this is summarized of SN20PD, all the steady state, but 20 photosensitive nanowire, we cannot resolve 40 photons because of the limited resolution of the Ytron. We can resolve 11 photons with high fidelity because there is a abrupt drop there. Okay, in summary, for SPDs, I've talked about detection efficiency and timing jitter. In particular, for detection efficiency, I talk about fractal SPD with reduced polarization sensitivity. And for timing jitter, I talk about 2 mechanisms of device timing jitter we contributed. And for SNMPDs, the central concept is to map the number of detected photons to the supercurrent in the reservoir, and it can serve as unfolded coincident counters, and also can serve as photon number resolving detectors with simple circuitry. With that, I would like to thank you for your attention. I'm ready to take questions.